what we have seen yesterday is the case of binary and Emery signaling in the baseband, or binary and Emery signaling waveforms, baseband signaling waveforms. All right. We have seen that in the Emery case, we can have the orthogonal. We started with the orthogonal set of signaling waveforms and give a number of examples of orthogonal signals. And since orthogonal signal sets can be taken as basis functions for any other signal set, it seemed reasonable to derive other signal sets from an orthogonal basis, right? And we in fact derived the other classes from the orthogonal class itself, right? For example, the simplex class and the biorthonormal class. The antipoderal signal can be thought of as a special case of the simplex class, right? Okay. Today we will take up the case of passband waveforms for binary signaling and Emery signaling. Of course, we will start with binary signaling today, and perhaps this and the next lecture will be both devoted to binary signaling, and then we will go on to the Emery signaling case. Now, passband signals basically are we can also call them band pass signals, are essentially those signals which have most of their energy or practically all of their energy concentrated around a non-zero carrier frequency, right? That is the basic idea, non-zero center frequency. That center frequency definition is a bit vague. That is, they contain no components at zero frequency. Essentially, that's what we mean by passband signals. And you must be remembering from your previous course in analog communication, or the first course that you have done, that such signals are very conveniently described in terms of a complex representation, right? And for the convenience that it gives, we will continue to use that complex representation. Just to recapitulate for you what the basic features of a complex representation are, I will just summarize for you some of the things that we will be, some of the notation and features that we will be using from complex representation. Okay? So I will start with a very brief review of complex representation of passband signals. Right? Complex representation. Okay, that's what we are doing just now. Basically, a passband signal can be represented in terms of an equivalent baseband signal using complex representation. This is the underlying point that you have to remember from your previous knowledge. That is, you can have actually for a passband signal a baseband representation, right, which will be generally a complex signal. Okay, that is, we can represent this as a baseband signal which has a real part and an imaginary part. Okay, the corresponding passband signal would be VRT cosine omega naught t or 2 pi f naught t minus VIT sine 2 pi f naught t, right. So corresponding to this baseband representation, the passband representation, which is of course a real signal, right, can be represented as in terms of what is called an in-phase component and a quadrature phase component. I am sure you have done all this, and I am just trying to remind you of these basic things. So VRT is therefore sometimes also called the in-phase modulation component, and similarly V sub I t is the quadrature phase modulation component, right? Or briefly, they are generally called in phase and quadrature phase components of the passband signal. Strictly speaking, if I were to call this, let's say, V prime t, then you can express this V prime t in terms of Vt by using a complex representation as follows. V prime t, the passband signal, is real part of your Vt, which I'll just write in the expanded form here, Vrt plus j V sub it multiplied with e to the power j2 pi f naught t. Real part of this whole thing. It's quite clear that the real part of this will be precisely the passband signal V prime t, namely Vr cosine of 2 pi f naught t minus Vi sine 2 pi f naught t, right? And in general, this passband signal will, if you were to look at it on an oscilloscope, will exhibit both amplitude as well as phase modulation, right? Because that's quite obvious from the nature of this signal, right? From the nature of this signal, if you were to write it purely in terms of a cosine function, then you can write it in terms of an amplitude modulation into cosine 2 pi f naught t plus a phase modulation term, right? You can rewrite this in that form by using the standard trigonometric identities. So in general, this hardly needs any elaboration. It will exhibit both amplitude as well as phase modulation. Please stop me, or if you have any questions, please ask the question. Now, the reason why we use this representation, this kind of representation, is basically for convenience. It's very convenient. For example, suppose you want to study the effect of a phase offset. Maybe the carrier and the receiver is not perfectly synchronized with the transmitted carrier, and you want to study the effect of a phase offset in the carrier or a frequency offset in the carrier, right? All you have to do is multiply this with e to the power j theta or e to the power j nu t, where nu may be the frequency offset, right? So complex representation is mathematically much more convenient to handle, and therefore it's preferred. So for example, a phase offset could be simply denoted at baseband itself without going to passband, right? You can take the baseband complex representation, let us say this one, and multiply it with e to the power j theta, where theta may represent the phase offset, right? Similarly, you can have a frequency offset, or both for that matter, where nu may be a frequency offset. So without going into messy trigonometric identities, which you will have to make use of if you were to continue to work with the real representation, it's very conveniently handled in the complex domain. Okay, that is one reason. And of course, as we will proceed, we will see the need for this more and more. Any questions so far about the review of complex representation? No, because it's all fairly simple and standard, and I'm sure you don't need much. This is a representation, a block schematic representation of how to obtain a complex representation of a passband signal, right? All you have to do to obtain the complex representation is to obtain the in phase and quadrature phase components, right? Because that is what these components basically define the complex representation, right? So you take your passband signal, which I am now calling Vt, right? You multiply the signal with cosine 2 pi f naught t as well as its quadrature carrier sine 2 pi f naught t. Low pass filter these and you will obtain your VRT and VIT, right. It is very simple exercise, that is, if you start with Vt equal to VRT cosine 2 pi f naught t minus V sub I t sine 2 pi f naught t, and if you go through this operations that are shown in this picture, at the output here, at the output of this low pass filter you will get V sub RT, at the output of this low pass filter you will get V sub IT, right. So given a pass band signal, we can obtain the complex representation practically using this method. Okay, this is a practical method of obtaining a complex representation, and then to continue to work with this complex representation in a physical real system. Okay, so complex representation is not only for just convenience in mathematics, it also introduces a lot of convenience in actual processing of these signals, as you can see here, because what you have done is, without loss of any information, you have represented the information content of the signal, which was earlier centered around f naught, to baseband, right, and that is a very nice thing to do from a signal processing point of view. Do you appreciate that? Why?
Sir,
yes.
there's one thing. Is this transformation from the passband to the baseband, is it a linear transformation?
Yes, because all the components, okay, to the extent that we are doing a mixing operation,
yeah,
but that mixing operation is essentially doing what? It is carrying out a frequency translation, nothing more than that. So even though strictly speaking it is not a linear operation, right, but the kind of operation that, in fact, even for all practical purposes, such an operation is regarded as a linear transformation. It's a linear modulation.
Like we carry out some operations on VR and VI separately and then reconstruct the signal. It will have the desired thing.
Because as you can see, from VR and VI I can go back to V, isn't it?
Yeah.
So therefore I have not lost anything, right. If I can go back to where I started from, that means I have not lost anything, right, and that is precisely the point here. But the question that I had put to you was, why should this be of some use to us from the signal processing point of view, from actual implementation point of view?
Because we can work in the baseband.
That's right. And that may be very important if, for example, you decide to do digital signal processing on the signals, right, because you have to sample the waveform and then process it, right, and your sampling and all that is taken care of much more conveniently at baseband than at passband. Although one can sample in passband also, but the sampling rates involved will be higher. But in this case, one can work with low sampling rates and therefore efficiently make use of digital signal processors which may not work at very high frequencies, right. So without any loss of information, you can represent it by a signal of this kind. Any questions on this? Okay. Now in digital communication we are going to have to work with signals which are essentially time limited in form in some sense, right, either strictly or at least for all practical purposes. That is, we are going to work with pulses. So the specific class of signals which are of interest to us here are pulses. So let's talk about passband pulses and their spectrum. Typically I can take a signal, so let me talk about passband pulses. First of all, what will passband pulses look like? You know what do baseband pulses look like? Let's take the example of a rectangular pulse. You know what a rectangular pulse looks like. What will a corresponding passband pulse look like? Any idea? Anybody would like to volunteer?
Passband pulses will be sinusoidal limited by
Basically it will be
sinusoidal this thing and modulated by square wave.
That's
Amplitude modulated.
Sir,
by
like the split
that will be amplitude
phase
modulated
code
with square wave.
was itself a passband type of thing.
sorry.
The split phase code, like it's also.
Yeah, but let's talk of a high enough carrier. So what will a pulse look
It
like?
will be number of cycles of a sinusoidal.
Basically, yes, you're quite right. It will be a gated form or a windowed form of a simple sine wave. Basically, that's what it is going to be. Okay, I got a picture here so that you can picture it better. Right? It's basically a finite duration sinusoid. That's all.
Yeah.
Right? Let's say between minus t by 2 to plus t by 2. Right? So a gated sinusoid. It's 0 outside this interval. Right? So if you were to define it mathematically, it is this sinusoidal function sine 2 pi f naught t or cosine 2 pi f naught t or whatever, or in the time duration between minus t by 2 to plus t by 2, and it's 0 outside. Okay, that's a passband pulse. And since in general its phase may be arbitrary, we can have a complex representation of this kind, a passband representation of this kind. Alright, so a passband, the general nature of a passband pulse mathematically is a real part or in phase part pulse. This is also a pulse. This basically now SRT is what? Some kind of a rectangular pulse, right? 2 pi f naught t minus SIT sine 2 pi f naught t. Okay. What will be the suppose I denote the Fourier transform of SRT by SR omega or SRF, and that of SIT by SI omega. What can we say about the spectrum of such a pulse using your properties of Fourier transform? This will have a displacement around f naught and 1 around SR here, right, SF plus f naught minus half similarly for S sub I. That's right. This should be j by 2. I have put that, that's why there should be negative sign here. SI f plus f naught. Okay. Okay. Can I proceed further? Fine. Let's just complete this discussion by writing an expression for the energy of a passband pulse. Energy EP, E sub p, which is of course defined as s square t dt between minus infinity to plus infinity. Now, by Parseval's theorem, you know that this will also be equal to integral of
X omega.
mod SF square df, right? You either take the energy in time domain or take the area of the spectrum magnitude square in the frequency domain. Now, through very simple straightforward exercise in which you express SF in terms of SRF and this expression that we have written here, use this expression for SF and make use of the fact that SF is essentially a passband signal, that is SRF minus F naught, and let us say SRF plus F naught will have no overlapping components, right? So when you come across a product of these two, what will be the product? Equal to 0, right? So making use of these kinds of identities, if you were to go ahead and do some simplification of this expression, it's very easy to check that this will reduce to, in terms of the real and imaginary parts, SRF magnitude square plus this I am leaving as an exercise for you to prove yourself. Simple but interesting exercise to do. and therefore in time domain one can again write this as equal to SR square T plus SI square T dt, again using Parseval's theorem once again. Okay. So I think that should be enough for a review of complex representation of passband signals, right? You have any questions? Please speak out if you have any questions.
Sir, this
Yes.
S of f being band limited,
Yes.
does it necessarily mean that SRF and SIF are band limited?
It's the other way around usually. Yes, of course, both way around it is correct, because of course the example that I got here of a pulse like this, since it has a rectangular envelope, right, in the sense that it is gated by a rectangular function and it has a strictly finite duration, the corresponding spectrum is strictly, what kind of spectrum you are going to get? Sinc function displaced to f naught and minus f naught. So it will really extend to infinity, right? And therefore the corresponding SRF and SIF will also be sinc functions.
Not exactly band limited, but okay.
Right? They will be similar. The shape of the SRF and SIF will be very closely resemble the shape of SF, right? One can do that exercise, obtain an expression for SRF in terms of SF. It's it will be very similar to, or it will be dual to the kind of expression you have here, where you expressed SF in terms of SR and SI. One can go ahead and write SR and SI in terms of SF, right? It will be an interesting exercise to do. Any other question? All right. Let's return to the main subject of interest to us here, namely passband waveforms for binary signaling. So we'll take up the case of binary signaling first, binary modulations first. Okay. Now to do that, what is different here as compared to the baseband case? In fact, if you were to look at the baseband, what are the schemes we had that we discussed? Essentially two in nature. I mean, broadly there were two classes, namely the antipodal class and the orthogonal class, right? And I think as far as binary is concerned, it's quite clear that the orthogonal class is only of academic interest, of not really of that great an interest. And so we'll do most of our discussion in relation to the antipodal class. So what did we have there? A baseband pulse shape PT, and both its that pulse PT along with its negative was serving as the two modulation waveforms to map either a 1 or a 0 onto one of these modulation waveforms. Okay. Now with the essential difference that we have is we are going to have a pulse which is passband in nature, right? And therefore the general representation of such a pulse is, we already seen, it has an in-phase component and a quadrature phase component. Now we can do one of the following two things. We can either use both components of the carrier, namely the in-phase and the quadrature, or we may use only one, right, for the construction of a waveform. Let's start with using only one. Let's say we're using only cosine 2 pi f naught t, right? It's quite clear that I can construct an antipodal signal from such a waveform by just multiplying this cosine 2 pi f naught t with some pulse shape and its negative, right? It's trivial. So a trivial kind of extension of the antipodal signaling that we have done for the baseband case to the passband cases, take the same pulse shape that you were using in the baseband case and multiply it with cosine 2 pi f naught t, right? So either pt cosine 2 pi of naught t or minus pt cosine 2 pi of naught t, right. So let's take the real part of the quadrature representation. So based on the real part representation, I could have an antipodal signaling scheme as the simplest possible scheme for the passband case, right. For example, pt cosine 2 pi f naught t as one signal and minus pt cosine 2 pi f naught t as the other signal. Just for the sake of simplicity, you could assume or you could try to visualize pt to be a rectangular pulse, just to visualize what is happening. So suppose we assume it is a rectangular pulse. Essentially it is constant over the time duration, whatever it is, minus t by 2 to t by 2, or let's say between 0 and t, just for the sake of simplicity. So what kind of a modulation scheme we get? You are familiar with this, I am quite sure. It is essentially what is generally known as binary phase shift keying. So the antipodal signaling in this case essentially reduces to also called simply BPSK. Okay. So because you are taking a carrier cosine 2 pi of naught t and you are either sending cosine 2 pi of naught t with 0 phase or with a phase of pi or 180 degrees, pi radians or 180 degrees. Alright. So you could as well have taken, of course, sine 2 pi of naught t with a similar result. That will also be BPSK. So that is the simplest kind of passband binary signaling you can think of, which is essentially an idea borrowed from baseband signaling. Only thing is you have embedded it onto a carrier. That's all. Nothing new about it. Fairly straightforward. In the more general situation, I could take both the in phase component and the quadrature phase components together, right? So the simplest way in which I can use both the components is as follows. When I say both components, I am referring to the in phase and quadrature phase carrier components. Use antipodal signaling on both the components, right? That's the simplest way. Just like I was doing it only on one of the components. Now how can we use this? We can use it in many ways. We can have two independent bit streams coming in, right? One modulating, doing a BPSK kind of operation with cosine 2 pi of naught t, right? And the other doing a similar operation on sine 2 pi of naught t, right? So one bit stream, there are two independent bit streams, let's say bit stream 1 and bit stream 2. Bit stream 1, the successive ones and zeros that are coming along in this stream will decide the successive phases of this carrier, right? Whether in a particular interval the cosine 2 pi of naught is going to go with a positive or a negative sign. Similarly, the consecutive bit values of bit stream 2 will similarly define the consecutive signs of the sign component, and whatever the two may be, two individual signs may be in a particular interval of t seconds in which both the bits are being looked at, you will have a composite signal which will be plus minus cosine 2 pi of naught t plus minus sine 2 pi of naught t, right, leading to plus minus cosine 2 pi of naught t plus minus sine 2 pi of naught t, assuming of course that we are using rectangular pulses. We may be using some other pulse shape, so in that case we have to put an appropriate PT or ST or whatever here. You may use the same pulse shape. There is no need to use different pulse shapes, but the signs of these pulses are independent from bit interval to bit interval. So that is one way of doing this. The alternate way of doing this would be, you have a single bit stream. Okay, when you have a single bit stream, what you can do is you can convert this into a not a binary system of individual bit streams, but a 4 array system, right? By looking at the incoming bit stream 2 bits at a time, right? Just like we were doing in the Emery baseband case earlier, and now deciding, depending on the combination, whether or not this has to go with plus or minus and this has to go with plus or minus, because there are 4 possible combinations and there are 4 possible set of combinations of these signs here, right? So you can get what is called quadrature phase shift keying, because essentially depending on what sign you have here, essentially you are finally going to have a carrier of frequency f0 with one of 4 possible phase values. Is it clear? Because sine 2 pi f0 t plus sine 2 pi f0 t will give you one phase. You know, as you change the sign combinations, you will get 4 different possible phases of the carrier that you might pick up to represent the 2-bit block that you want to transmit. Very simple, and I don't think you have any questions. So you can construct either 2 independent binary modulations out of this, or you can construct a single quadrature modulation out of this, right? And because the second method is more commonly the choice, we will basically talk about QPSK. So let's go through a bit of exercise for a formal representation of QPSK that we have just discussed. We can basically represent this as a single complex waveform, baseband waveform, even though it's a passband modulation. That's the whole idea of complex representation. You express in terms of baseband. You don't have to keep on talking about the carrier all the time. Okay? Carrier can be just thought of as being in the background. You don't have to keep explicitly writing it. So the transmitted waveform, the composite transmitted waveform CG, is a succession of pulses with complex amplitudes A sub L and pulse shape ST minus LT, right? Mind you, these ALs are complex amplitudes. What has gone in the background is cosine 2 pi f0 t and sine 2 pi f0 t, that is embedded in this representation. AL, because I'll say AL would take on one of these possible values. It could be 1 plus j times some amplitude A. It could be 1 minus j times amplitude A minus 1 plus j times amplitude A and minus 1 minus j times amplitude A. For example, this could be the case when your Lth bit pair, we are considering now Lth bit pair, which we are assuming is coming over a t second duration, right, is, let's say 1 1. I have taken any arbitrary mapping here, although there is a practical reason for doing this mapping also in a particular manner called the Gray code. We will talk about that separately. So if your input bit combination is 1 1, you may choose AL to be like this, 1 0, you can choose AL to be like this, and so on. What is in the back? So this is only the pulse shape. ST describes the pulse shape that you may use. If you take a rectangular pulse, ST is a rectangular pulse, both for in phase component as well as for the quadrature phase component, right? And what is gone in the background is the carrier. Well, if you take If you want to bring the carrier into the picture, all you have to do is multiply Ct or this whole thing with e to the power j2 pi f naught t and take the real part of that. Right? You will get back your same old expression. Fine? So, do you all understand this complex baseband representation of a passband QPSK signal? Is there any problem about it? Anyone? Fine. Alternatively, it is also a bit educative to look at the same thing as follows. Instead of writing A sub L into S t minus L t, let me first introduce impulse functions as if the data is coming in the form of a series of impulses, right? And then these impulses are shaped by a filter with impulse response ST, right? That's an alternative way of looking at it. Where this ST is what we had earlier put over there. So this very clearly brings out the role separately of A sub L's, which represents the data complex. Now the data is being represented in a complex form. 1 plus j, 1 minus j, etc. corresponds to what particular bit stream, bit pair of values you are getting in the lth block, right? And this brings out the role of pulse shaping at the transmitter. Now I have got a picture which summarizes all this discussion in the form of this diagram. I have got two pictures here. This is what is called a complex constellation diagram or a signal space diagram for QPSK, right? Essentially represents the data points, the location of the data points of QPSK, right? More specifically, you may remember that 1 plus j will be which point? This one, right? Let's say this is 1 and this will be 1 here also. So this point is representing 1 plus j. So this is a representation for bit pair value 1 1. Do you remember this which I wrote here a few minutes ago? Okay. So this is, I have just taken any real axis, any imaginary axis, and I am trying to represent this complex data onto the signal space diagram like this. So this point indicates 1 plus j and essentially therefore represents the bit pair 1 1. Therefore what it does is it gives you a mapping of bit pair values to these, one of these 4 points on this complex constellation diagram. Similarly 1 minus j will be this point, right? 1 minus j is this point. This is being represented by 1 0 in that this is minus 1 plus j, that is 0 1, and this is 0 0. Okay. So this is one way of representing the QPSK signal. You can think of the real and imaginary axis also as essentially an axis which corresponds to the carrier, in phase carrier cosine 2 pi f naught t and the quadrature phase carrier sine 2 pi f naught t, right? And therefore now it will come out very clearly that when I take this point, what I am really doing is transmitting a carrier phase of how much? What is the carrier phase corresponding to this point? Pi by 4, isn't it? Cosine 2 pi f naught t plus sine 2 pi f naught t, right? That will correspond to cosine 2 pi f naught t plus pi by 4. Okay. Similarly for this will be minus pi by 4, this will be 3 pi by 4 and so on. Okay. So you can think of these 4 points as representing 4 different phases. Actually you can imagine a circle on which they lie, right? You can imagine a circle on which these 4 points lie. And this circle representing different points in the circle, essentially representing the carrier with a different phase, right? This is cosine 2 pi f naught t with 0 phase, with 45 degrees, 90 degree, and so on. And this is a picture for the representation I derived later. The data bit pair is coming along, from which you obtain a complex impulse train, with amplitudes either 1 plus j or 1 minus j or minus 1 plus j, and that impulse train, this complex thing is being represented by two signals here, right? The real part and the imaginary part, that goes through a pulse shaping filter to obtain the complex waveform. Of course, before final transmission, you will convert this complex waveform into a real waveform. And how will you do that? Multiply the real part with cosine 2 pi f naught t, the imaginary part with sine 2 pi f naught t, and add them up. Add them up or subtract them, whatever is required, right? So you do the processing in the complex domain and then come back to the real domain and transmit, of course, only one signal rather than two signals. Now, if you were to look at a typical plot of course, just to complete the discussion, these pulse shapes may not be in general rectangular. In practice, they may be band limited pulses. For example, they may be Nyquist pulses, right? So, in that case, it is more difficult to visualize the picture in terms of a waveform, because the phase is not exactly constant throughout, right? If you have a non-rectangular pulse, the phase is not exactly constant, because it is no longer a pure cosine waveform. It is a cosine waveform which is modulated by or gated by some kind of a time varying pulse shape, right? I mean some kind of a time variation depending on the pulse shape. Okay. Now, if you were to take the case of, I have got a picture here, try to imagine a QPSK waveform with rectangular pulses, just for the sake of simplicity. Let us see what we will see. I find a lot of people feeling very sleepy today. Is it my lecture or is it something else? I am putting you off to sleep. Doesn't speak highly of what I am doing here, but anyway, let us continue. This is a typical waveform that corresponds to QPSK. I want to bring out an very important feature of this waveform, which I like you to appreciate nicely. It's not a very good plot that I got here. I wish I had a better plot. I have taken a carrier with 0 phase here, corresponding to, actually apparently I have taken the phases to be 0, 180, 0, 90, 180, 270 and 0. I mean basically these 4 phases. Although according to that picture I should have taken 45, 135, then minus 1, which will be how much? 225, and then whatever. Whatever it is. I am sure you can all calculate it, right? So I have only done it, I have done it perhaps wrongly, but it doesn't really qualitatively affect the argument that I want to give. Here I got 0 phase over t second. Mind you, this t seconds corresponds to how much? Time for 2 bits, or time for what is sometimes called a die bit, right? It is not bit period. Bit period will be t sub b, which will be equal to t by 2. You are looking at 2 bits together and then transmitting one phase of the carrier, right? Then again I have got a 0 degree here, and here I have got a change of phase. I have got 180 degree phase change. Then I got at this point I have got another change of phase by 90 degrees, and so on. So what you will find is every t seconds there is a possible phase change, right? There may be a phase change, there may not be a phase change, depending on the successive bit combinations that you get, right? and these phase changes can take on values of how much? I think that's very easy to appreciate. What are the values of the phase changes that you will see in this waveform? Come on. Values of the phase changes that you might see at these points.
90, 180, 270.
That's right. Well, 90 and 270 are same thing, either plus 90 or minus 90. Right? It's the magnitude that is really of interest to us to worry about. The maximum phase change that you can think of is 180 degree. Right? Either plus 180 degree or minus 180 degrees. Right? Alright. So what do you see? That you can have as large phase changes as 180 degrees at the points of going from one dye bit to another dye bit. Now that essentially means that in reality you will never get rectangular pulses no matter what you do, isn't it? Because rectangular pulses means infinite bandwidth. In reality you will always be doing some band limitation. The moment you do band limitation, these are not going to be sharp transitions. So what is going to happen to these points when you do a band pass filtering of such a signal before you finally transmit it onto the channel? It will go through a zero amplitude because there is a, the envelope really becomes zero here, right? So I think the envelope will perhaps stay constant here, and at this point it will certainly go zero because of a 180 degree phase shift. That is something that I think I would like you to appreciate. Now, which is very undesirable.
This is not clear, sir.
This is not clear.
So, because after every time period, after every dye bit period,
The moment there is a
from zero phase, we have to come back to zero.
Let me put it this way. The moment there is a discontinuity, right, that discontinuity will tend to be smoothened out by the filter. The filter is going to do band limitation. In time domain, the equivalent effect is smoothing out the sharp transition. And how will that be done? By making the waveform rounded. The decay will not be an abrupt one, but a rounded one. Right? That's a very crude picture I am giving. Exact effect you can calculate mathematically. Right?
So the only thing is that the decay will still has to start from the point where the discontinuity.
Okay, there may be a time delay. You are right. There may be a time delay.
In fact, this time delay thing has always been a problem. Like we make a thing anti-causal every time and say there will be a time delay.
Yeah. Is there anything wrong with that?
Could you take it up in some Thursday class? Like.
All right. I can take it up even here. There is no problem. If necessary, I can take it up here. But yes, that can always be done. Any anti-causal system can be made causal by introducing sufficient amount of delay in the system, right? Although I am not talking about anti-causal, all I am saying is, okay, what you are saying is that the filter will take some finite time to respond to an abrupt transition. Sure. And therefore, physically you will not see this rounding immediately after this occurs, but it will continue over some interval. I agree with you entirely. Nothing wrong with that. Therefore, the precise point at which zero will come will not be at this point, will be slightly later, because the filter has a certain response time, has a certain time constant, which defines its bandwidth.
And by that time, the next dye bit has started.
Yes, the response to that also will be slow, right? After all, the response time is dependent on the time constant of the system. Everything is divided by the same amount, roughly speaking, very crudely speaking, right? Although this is best handled analytically. Right? Take the filter impulse response, look at the input and calculate the output waveform. That's the best way to handle it, but I am just giving you a very rough, crude picture of what you might expect to see, waveform wise. I am not going to through a calculation here, but what you can expect to see is a zero crossing. I mean, your waveform is going to actually have zero amplitudes at times. This is the important point. I mean, normally when you think of a QPSK signal, you think of this as a constant amplitude signal, right? And that's a desirable thing to have in a communication system, a constant amplitude signal. Do you know why? Any reason why? see, if you look at just this QPSK waveform, whatever, however badly it may be drawn here, it might first give us an impression, a rather deceptive impression, that it's a constant amplitude signal, right? And in general, it is, the next statement I'm making is, it is desirable to have a constant amplitude signal in a communication system. Why?
Additive noise will
So noise.
No, noise is not the main reason.
Non-linearity doesn't.
Nonlinearity is one thing, but even more important than the nonlinearity is the fact that your power amplifiers through which you are going to send these signals are going to work most efficiently if you work them at a specific level of amplitude or power, rather than having a large dynamic range of variation. The power amplifiers will not be very efficient if you allow a large amplitude variation in the output. Secondly, the nonlinear effects will be more pronounced when the envelope is not constant. Now that is something that will take time to appreciate, but yes, that point is, I think it's more or less should be clear.
Yes, sir.
I mean, if there is a nonlinearity in the system, then the system will respond with different gains at different input amplitude levels, right, rather than a constant gain. So it's best to have a constant amplitude of operation, so that you are working at a specific point on your nonlinear system and around which you may expect a linear kind of behavior without any problem, right? So from both a nonlinearity presence point of view as well as from efficient power amplifier point of view, it is preferable to have waveforms in a communication system which are essentially constant amplitude waveforms, right? And QPSK signal to start with looks like such a constant amplitude waveform, right? But in reality, after filtering, it no longer remains one, right? So which means you are likely to have nonlinear problems, nonlinear effect problems, and also power efficiency problems. So this is something to keep in mind. What would you like to do to take care of this? Now there are a number of things people have tried to do, but as a simple straightforward improvement, one can do something here immediately by slightly changing the scheme of things. You have QPSK, you continue to have QPSK, but what you do is, instead of having a bit transition every t second, a phase transition every t second, the I and Q components are phase offset by half of this t, or bit interval. So that now phase transitions will occur every TB seconds or every t by 2 seconds, but the magnitude of phase transition will be limited to 90 degrees rather than 180 degrees. So that sharp discontinuities of very high, very abrupt kind will be avoided.
When you say they are limited to 90 degrees,
We'll take it up next time, because we are running short of time now, when we discuss what is called offset QPSK. So it's a child of QPSK which has slightly more desirable properties than QPSK in this manner, in this respect. We'll start from here next time. Thank you.